Welcome to the presentation of LidarCLIP, or How I Learned to Talk to Point Clouds. This is a collaborative work between Georg, Hess and Tonderski, supervised by Christoffer, Petersson, Kalle, Åström, and Lennart, Svensson. The core motivation behind LidarCLIP is that CLIP is awesome, and we want a CLIP that works with LiDAR. CLIP has generated many downstream works, the most famous of which is probably DALI 2, but there are also many other applications, for example, this zero-shot segmentation approach, MassCLIP. However, we cannot directly train a LiDAR CLIP in the same way that CLIP was trained, because there are no huge datasets of text LiDAR pairs available online. However, in the autonomous driving industry, there are huge datasets of image LiDAR pairs, and perhaps we can use images as intermediaries to connect text and LiDAR. This is the core idea behind our work. Our contributions are fourfold. First, we show how to encode LiDAR into an existing CLIP space. Next, we demonstrate that these LiDAR embeddings that we can generate with LidarCLIP are complementary to the vanilla image CLIP encodings. We demonstrate that we outperform prior works on zero-shot classification and retrieval, and we also demonstrate a number of off-the-shelf generative applications. This is a demonstration of regular CLIP, which is trained on large online datasets of image text pairs, where separate text encoders and image encoders are trained to embed the corresponding sentence and image into a common space using a contrastive loss objective. We use the pre-trained CLIP exactly as is, with frozen weights without changing anything at all. And then we move to the automotive setting. Here we have large datasets of image LiDAR pairs. So we take the frozen image encoder, embed a corresponding image, and then we train from scratch a LiDAR encoder to embed the corresponding point cloud to exactly the same embedding as the image. We use a regular mean-squared error similarity loss. Notably, no gradients are propagated to the image encoder. This means that the LiDAR embeddings will also be trained to map into the original CLIP space and should therefore be compatible with any CLIP application off the shelf. Now that we have pre-trained our LiDAR encoder, we can do a number of different things. Here we show an example of retrieval. So given a single text prompt, which would be the retrieval query, we can embed it using the CLIP text encoder, and then we can embed our entire dataset of LiDAR scans that we want to search in separately using the LiDAR encoder. And then we simply perform a similarity ranking where we find the LiDAR embeddings that are most similar to the text embedding and retrieve the top K ones that we're interested in. Optionally, since we have pairs of LiDARs and images, we can also use the image embeddings here to get even more powerful retrieval. We can also turn this around, and we can take a single point cloud and embed that using LidarCLIP to get a LiDAR embedding, which we compare to a number of different text prompts. This that we show here is an example of zero-shot classification, where by finding the text prompt that are most similar and normalizing the similarity scores, we get essentially a probability distribution over the classes of interest. We can also take the same LiDAR embedding and run it through a couple of off-the-shelf, freely available methods that have been developed to work with regular CLIP to perform either text-to-image diffusion or image-to-text captioning. By replacing the inputs of these two methods with a LiDAR embedding instead, we get a for free LiDAR to image generation, as you can see on the left, and LiDAR captioning, as you can see in the middle. Next, we demonstrate qualitatively a number of retrievals using only the LiDAR embedding from LidarCLIP. On the left, you see the text prompt, tuk-tuk, busy intersection, and bus stop. And then you have the four most similar examples. Here we show the images, but we of course retrieve these using only the LiDAR embedding. As you can see, LidarCLIP can retrieve a number of different scenarios, from strange objects to general scene conditions and static environments such as bus stop. However, sometimes it fails. As you can see, the fourth retrieved example for tuk-tuk is actually some kind of van. Next, we try to push LidarCLIP to see if it's able to retrieve scenes that are not typically associated with LiDAR data. Here you can see various lighting conditions, such as bright and sunny, sunrise, night, and headlights. As LiDAR is an active sensor, it produces its own light. It's not obvious that the information about the general sun or lighting condition is available in the point cloud. However, somewhat surprisingly, LidarCLIP is able to retrieve these scenes relatively well. Perhaps most surprising is how well it can retrieve scenes with many oncoming headlights. We also demonstrate retrieval quantitatively by constructing a retrieval task from the one's dataset. Here we make use of object-level annotations, both 2D and 3D, as well as metadata for each scene, such as time of day, weather conditions, etc. We compare with two prior methods, point CLIP and CLIP to point, which both use CLIP to perform zero-shot capabilities on point clouds. However, as these are not designed for scene-level retrieval, they struggle quite a bit on this task. In contrast, both vanilla image CLIP and LidarCLIP, as well as our joint approach, work relatively well, where the joint clearly outperforms both image and LiDAR-only retrieval. Interestingly, where we look in more detailed results for the different classes or categories, we show that LidarCLIP is able to outperform image CLIP significantly on nearby objects, but perhaps expectedly is struggling more on time of day and weather. Here we demonstrate a highly useful real-world application for autonomous driving. The objective in this task is to retrieve a corrupted image of a nearby pedestrian. If we naively construct this query prompt and pass it to either LidarCLIP or LidarCLIP, we will almost certainly get only corrupted images or only nearby pedestrians, since the information about both these things at once are not present in one of the modalities. If the image is really corrupted, we will not know if there's a nearby pedestrian, and similarly LidarCLIP or the LiDAR data is not aware whether the image is corrupted or not. However, we propose to use separate prompts for the separate modalities. So for a pair of images and point clouds, we query the image for the prompt a corrupted image, and we query the point cloud for the prompt a nearby pedestrian. And then by ranking these scores jointly, we're able to retrieve scenes that the image believes are very corrupted and the LiDAR believes are very highly to contain a nearby pedestrian. And you can see an example of this on the right side. Here there is a huge amount of flare and visual distortions in the image. You can barely see the legs of one of the pedestrians, but the other pedestrian is completely invisible, whereas in the LiDAR data, it's very clear that there are nearby pedestrians crossing the road. These scenes are highly important for both evaluation and training of autonomous driving systems, as they are very safety critical and could lead to an accident if not handled properly. Here we dive into the LidarCLIP architecture. On the left, you have a point cloud, which is discretized into bird's eye view, and all empty cells are discarded, generating a set of input tokens that we pass into a transformer, in this case the single stride transformer architecture, to extract features for each token. Next, analogous to original clip, we simply pool all the features from all the different tokens into a single global clip feature. And this is the one that we optimized during the LidarCLIP pre-training. We can also skip the pooling step and simply rearrange the tokens back into the original bird's eye view space. In this sense, we generate a localized clip feature for each 3D cell. We demonstrate the quality of this localized representation here using voxel-wise zero-shot classification, or perhaps zero-shot segmentation. On the left, you see a heat map of the prompt, a bike or a moped. And you can see the LidarCLIP lights up in 5 distinct spots. By cross-checking with the image, we can see that these 5 spots actually correspond to 5 visible cyclists. This is quite impressive, as LidarCLIP has only been supervised with a single global 2D pooled feature. And here we can see that it's able to lift this to 3D and generates relatively local, meaningful 3D clip features. We exploit this to perform a zero-shot classification task. Again, we embed the entire point cloud, but this time we make use of the bounding box annotation to only extract the voxels that are inside or overlapping with the bounding box in question. Then we pull these to generate an object feature and perform zero-shot classification as described earlier. We compare with point clip and clip to point again, now in a setting which these methods have truly been designed for. Nevertheless, LidarCLIP outperforms them significantly and performs closely to an image clip, which is able to zoom in and look at high-resolution zoomed-in crops for each object. Notably, combining LidarCLIP with a zoom-in image clip leads to even better performance, as is demonstrated by the joint line at the bottom. Next, we demonstrate a couple of generative applications. On the left, you have the original image and the corresponding point cloud. In the middle, you have a generated image based only on the LiDAR embedding. We also have the corresponding caption, again based only on the LiDAR embedding. Finally, we can generate an image condition on both the LiDAR encoding and the caption. Here we have another example. The image generated solely based on the LiDAR encoding is not quite really realistic, but captures the essence of a person walking sideways to the camera. The caption is quite accurate, a man walks on the street. And finally, the image generated based on both the LiDAR encoding and the text encoding is perhaps not photorealistic, but more reasonable. In summary, we propose LidarCLIP, a way to connect LiDAR and text and images. We show that LidarCLIP is complementary with ImageCLIP for both retrieval and zero-shot classification. We demonstrate effective multi-prompt retrieval, where we query images and LiDAR separately to find very rare and very valuable training or evaluation scenarios. We show that LidarCLIP learns locally meaningful 3D features from only 2-dimensional clip supervision. And finally, we demonstrate a number of generative applications. Thank you for listening, and please check out our GitHub and reach out to us if you have any questions.